Started. Um, Before we get back into two-way Anovas, I want to know if you have any questions about your one-way Anova report. How's that going? I've gotten a couple of questions from people about some scripting issues that they were having. Is there anything you want to talk about now about that? You guys have started, right? Oh my God, please tell me you've started. Yeah, so get started. So I was working through, I put the P's analysis up on the Moodle site. So I created a R Markdown version of the P analysis that we spent a lot of time working through in class. To go from the script that operated to the Markdown document took me probably a couple of hours of tinkering with it yesterday to get it so that it looked decent when it finally got printed out. It's another one of those cases where doing a lot of the base scripting was actually pretty easy, but then getting a figure that I was happy with in terms of being able to see all the axis labels and things like this took me a little while of tinkering. It wasn't that I was doing a lot of novel coding for it, novel scripting for it. It was just that it didn't look right, and so I had to go back and tweak it, and then it still didn't look right. I had to go back and tweak it, etc. So don't get started on it so late that when it comes time to create the documentation that you need, writing the report and everything else, that you haven't allotted yourself enough time to get that done. Get started on that when you get a chance. All right, so we're
Just a quick question on that.
Yeah.
Your report that you put out there on Moodle,
Uh-huh.
are you looking for something similar?
Yeah. The whole point of that was so that you kind of have an idea of what I'm looking for.
Okay.
So the report, especially for this particular one, because it's a relatively simple analysis, the report doesn't have to be huge. What I want it to be is I want it to be complete, I want it to be understandable, and I want it to be, concise. So yeah, that's the thing. You want to set. There are three parts of it that I talked about. This introduction. And it's not like an introduction like you would write if you were writing a scientific paper or something like that. The introduction is basically your way of telling the person that you're doing the analysis for, this is how I understand the questions that you have for me as I look at your data set. This is what I understand you want me to do with these data that you gave me, because that will clear up for the person receiving the report, oh, this person really didn't understand what my questions were, so I need to go back and talk to the statistician because he's analyzing the data in a way that isn't kind of the way I was thinking about it. So this makes clear what your understanding of the data are. Or it is, I guess that's is. So whenever I occasionally get, well, not occasionally, like every year, I get biology and chemistry students coming to me with their senior thesis data. So they've been collecting data for the last year and a half. They have their data. They don't know what to do with it. And when they come to me and they want help analyzing their data, the first thing that I do is I sit down and I have a long conversation with them trying to figure out what it is they were trying to do, what are their data, how are their data coming from their experiments, and kind of what their overall questions are. And I write all this stuff down in a notebook where I keep my notes, and then I send them away, and they're very unhappy when I send them away because I need time to kind of process that, put together a script, get the analysis done, and then I schedule another meeting for them to kind of walk them through what I did in terms of their analysis. And so I spent a lot of time trying to get my brain wrapped around what it is that they did and what the questions are that they have, especially if they're doing something like in molecular biology. I'm an ecologist, I'm not a molecular biologist. I know how to do data analysis, but I don't have much of an idea of what kind of biology it is that they're doing. So I try and get that best understanding that I can get, and then I want to communicate that understanding back to them so that they can correct any of my misconceptions that might ultimately influence how I go about analyzing the data. So this first part is just stating, this is my understanding of what your data are and what you wanted me to do with them. Then there's the statistical methods. So given that understanding, this is what I did. This is where you include the methods. You also include any sort of data transformations that you needed to do, et cetera, et cetera. This is where you report alpha levels that you're using to make decisions. Maybe the people that you're working for wanted you to use an alpha level of 0.1 rather than an alpha level of 0.05 for decision making. That's where that would appear, et cetera, et cetera. And then the last thing is the results. And this is where you put all your statistical results. What did you find? Were there differences? What was the nature of those differences? And then this is where you also put in any tables and figures and things like that. So it really is just a three-part thing. And in the P's analysis was pretty straightforward. And so this results section was, I think it was like a four-line paragraph. So, once again, students, when I ask them to write a paper for me, or when I ask for these things, they're like, well, how long does it need to be? I'm like, well, it needs to be as long as it needs to be. If it needs to be 3 sentences of results, and that's all it takes to describe the results fully, it can be a 3-sentence result. That's fine with me. I've seen there's a paper we read in my first year biology class. The results are a single paragraph. And the students it was published in the journal Evolution, a very good biological journal. And the students are like, shouldn't the results be longer than that? Like, were there any results that were left out? No. Did you understand the results fine? Yeah. Then I guess that was how long the results needed to be. So I'm not looking for a particular length. I want you to explain fully what you did and explain fully what you found. And then when you're done, you're done. Does that help at all?
Yeah.
Okay, cool. All right. Yeah, so that's meant as a template for you. As we're doing a two-way analysis of variance, so you're going to write a similar report on a two-way analysis of variance. That report's probably going to be more involved because the analysis is more involved. When you do an analysis of covariance at the end of the semester, that's going to probably be a very involved report because, whenever I do an analysis of covariance with students, I have to spend a lot of time actually getting through their head what an analysis of covariance does before I can then proceed to explaining what the results of the data analysis are. So it just depends on what type of analysis you're doing in terms of how much time you need to spend explaining it. So that's that. All right, so we're talking about two-way Anovas at this point. In many ways, it's just like a one-way Anova, except that the calculations are a little more complicated because you now have 2 factors that you have to think about rather than 1 factor. This particular example, we have rats that were fed 2 types of fat, and then we're looking at their growth, and so their weight gain, essentially. And so we can begin by calculating the sum squares total. Sum squares total is calculated the same way that you would calculate sum squares total in a single factor analysis of variance. You find out what the grand mean is, and then you subtract that grand mean from each of the individual values, all of them, in this case, all 12 of them, and you square that difference. So it's the difference between the individual values and the grand mean squared, added up across all of the treatments that you have. So you would take 709 minus 597, square that, 679 minus 597, square that, 699 minus 597, square that, 657, 594 and 677, each of those minus that squared. That's the sum squares total. It's just like it was in a single factor analysis of variance. Then we have sum squares residual, or sum squares error, or sum squares within is how we also referred to it back when we were talking about a single factor analysis of variance. And the sum squares within is the within sample variation. So to calculate sum squares within, that would basically be this minus its mean, this minus its mean, this minus its mean, each of those things squared and added up. And you would add that up across this category, this category, this category, and this category. So in this case, it's the individual values minus the sample mean, not the grand mean, squared. And we do that for that, and that, add them all up. This is the sum squares within for this category. This is the sum squares within for this category. This is the sum squares within for this category. This is the sum squares within for this category. So remember that residual variation, residual is just kind of what's left over. It's the variation that is not explained by your factors. So if this is, well, if 11,666.67 is the residual sums of squares, if we add that to sums of squares subgroups, (7757.025) should be the total sums of squares. So let me check that. 775025 is the total sums of squares. So how did I get to that? What is this sums of squares subgroups? Well, in this particular analysis, we have males that ate fresh fat, males that ate rancid fat. We have females that ate fresh, and we have females that ate rancid. And for each of these subgroups, so in this case we have two factors. Each factor has two levels, so we have four subgroups. And so in each of these cases, each of these subgroups has a mean, 695.67, 535.33, 642.67, 517.33. Now, when you look at these means, you immediately start to think, oh, something's going on with these means. What's happening with these means in terms of what's the effect of sex and what is the effect of fat type on these means? If you just look at the means by themselves. If you look across fat type, if you go and look at all the fresh and all the rancid, what does it look like is happening when you look down here at the column means? Yeah, fresh gains more weight than rancid. If you look across male and female, which are the row means, what do you see? Males seem to be growing more than females, but the difference is not nearly as big as the difference between fresh and rancid. And so there's a certain amount of variation in your data that is systematic variation, that is variation due to the fact that the data are divided up into these different treatments. And so that's what the subgroup sums of squares are. It's basically taking the subgroup means minus the grand mean, which is 597.75, squaring that, squaring that, squaring that, and then multiplying this times the number of rows that you have and the number of columns. Sorry, the number of rows that you have and the number of columns that you have. And so, sorry, no, sorry. The number of treatment levels times the number of replicates that you have, 2 times 3. So to look at males and fresh, in sex, for example, so you have Let me make sure that I'm saying this right. Let's go back. Let's go back a level. Let me make sure that I'm telling you the right way of calculating it. Yeah, this whole thing is multiplied times what your operational sample size is. So you have 3 replicates in each one, 1, 2, 3, and so for each of these, you weight each of these by sample size in the same way that the sum squares among in your previous Anova is weighted by sample size. So each of these is multiplied times 3, or you can do the whole sum and multiply that sum by 3 since they're all the same sample size. So if you look at this equation, it's the sum of this minus that squared plus this minus that squared plus this minus that squared, this minus that squared, all multiplied times 3 is what gives you the subgroup means. So what that means is that the subgroup variance is 65,903.58. So what that variation is basically saying is that this is how much variation there is. If you look at the overall grand mean, how far away from the grand mean is the male fresh mean? How far away is the male rancid mean? How far away is the female fresh mean? And how far away is the female rancid mean? So it's basically saying there's a total amount of variation in the data set that is due to the fact that you've divided the data set up into these different treatments. Now, part of that variation is due to fat type. Part of that variation is due to sex of the rats, and then part of that variation is due to the fat by sex interaction. So when we look at sum of the squares total, not sum squares total. When we look at sum squares row, sum squares column, and sum squares row by column, these 3 things, 37, so I'll just put what they ended up being. Rows is, in this case, sex. So sum squares rows is 3780.75, 3780.75. Columns is 61,204.083, and the interaction is 918.75. So if we add 61204.083 plus 3780.75, and then add 918.75 to that, whoa, 65903.58. So basically, there's a certain amount of variation that is accounted for by the structure of your experiment. The question is, how much of that variation is due to differences among fat type, how much of that variation is due to differences among sex, and how much of that is due to the interaction of the two. So these three things should add up to what is the total amount of systematic variation in your data. So then the question is, well, how do we quantify each of these things? Well, it's easy enough to quantify subgroups. It's just this mean minus the grand mean squared, 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 added up and weighted by the sample size. That's easy to do. Well, in the same way, sum of the squares due to fat is easy to calculate. How do you expect you would do that? How would you calculate that? Based on how we've been doing these types of calculations. Is the effective fat in column means or row means in this case? We have fresh and rancid. Here are the column means. Male and female, here are the row means. Is the sums of squares fat going to be operating off of column means or row means? Column means. So what would we do? We want to see how the average of all of the individuals that were eating fresh fat, how does that differ from what? Well, not from rancid. We always compare the means of the treatments to what? One another or to something else? I erased it. When we were doing sum squares total, we compared each individual data point to what? The grand mean. When we were doing sum squares subgroups, we took each subgroup mean and compared it to what? The grand mean. So if we want to compare the means of fresh and rancid, what do? We compare those means to the grand mean again. Yeah, so this would just be this column mean minus the grand mean squared plus this column mean minus the grand mean squared. Once again, in this case, multiplied, weighted by the sample size. And in this case, the sample size here is 6. And so if we go and look at the calculation that I've done for columns, you will see that in the equation up here, it is, well, let's highlight the equation so we can see the colors. Here we have this minus that squared, and we have this minus that squared multiplied times 6, which is the sample size which both of those is based on. In the same way, if we want to know what the sums of squares due to sex are, we can come down here and highlight this one here, and we can see, as you would expect, it's just the row means, because the row means are for male and female. 615.5 minus 597.75 squared plus that one minus that one squared multiply times, once again, the number of observations that form the basis of those two means, which is 6 in this case. And that should give you your sums of squares due to rows. And so if you know what the sums of squares due to one treatment is, and you know what the sums of squares due to the other treatment, then you can basically subtract those two things from the sum squares due to subgroups, and that will give you whatever variation is left over that is due to the interaction of these two. So you can use the fact that all of these things have to add up to this to calculate what this one, and that turns out to be the easiest way to do it, is just by subtraction. Once you have all of these different pieces, you have everything that you need to know to calculate an Anova table, to put an Anova table in place. So what you need for the Anova table is you need the sums of squares for the row, which in this case is sex. You need sums of squares for column, which in this case is fat. You need the sex by fat interaction. You have error already, or the residual, what I've been referring to as the residual term, and you have the total sums of squares. Total sums of squares, sums of squares due to sex is taken from here. And you can see these are just actually keyed to where they are in the calculations that I've done. There's the sums of squares due to columns. Here's the interaction term, which is there. And then we have sum of squares residual. And when you look at the sum squares residual, you can see that this is just the sum of those things. But when you look at each of these things here, this is just, once again, this minus that mean squared, this minus that mean squared, this minus that mean squared is where you got this value here. So it's the same thing that we did in a one-way ANOVA. You're comparing, in some cases, individual values to the sample mean, which is where you get sum squares within. In some cases, you're comparing individual values to the grand mean. That's where you get total sums of squares. You compare row means to the grand mean for sum squares rows, column means to the grand mean to get sum squares column, and all of the means to the grand mean to get sum squares subgroups. And once you have all those things done, you have all the information that you need. The degrees of freedom are always going to be 1 minus the number of treatment levels. So for the rows, you have male and female, so 2 minus 1 is 1. You have 2 fat types, so degrees of freedom is 1. You have 11 total degrees of freedom, which is the total sample size minus 1. You have the degrees of freedom from sex multiplied times the degrees of freedom for fat to give you the degrees of freedom for the interaction. And then so whatever is left over is residual degrees of freedom. So once again, these things should all add up to the total degrees of freedom. You do the sums of, you calculate the mean square the same way. Mean squared is just the sums of squares divided by their sample size. So in this case, the mean square doesn't change for sex, it doesn't change for fat, it doesn't change for the interaction. It just changes for the residual because you have 8 degrees of freedom, which then reduces the mean square for the residual. To test each of these, you calculate an F statistic. That F statistic is just the mean squared of the effect divided by mean square residual, and it's that way for sex, it's that way for fat, it is that way for the interaction term. So it's the same thing. F is always mean squared treatment divided by mean square within, or residual, or whatever you want to call it. Some people call it mean square error. Doesn't really matter. It's that within sample variation that we're talking about. And then we know what the degrees of freedom are for this. So we would evaluate this at 1 degree of freedom and 8 degrees of freedom. 1 degree of freedom in the numerator, 1 degree of freedom in the numerator, and 8 degrees of freedom in the denominator. And then we would go and look that up in an F table or go to Daniel Soper's website, or we would just have R calculate it for us directly. And when we find the p-value, we find that there's no effect of sex. Even though there are differences in sex, those differences aren't big enough relative to the amount of variation within sex to show up as being statistically different. That should also not be a surprise to you because the amount of variation that was due to differences in sex is relatively small, and the amount of variation that is due to differences in fat type is huge. And that actually turns out to be the thing that is important. 2 times 10 to the negative fourth. This is the p-value for the effect of fat type. That is a highly significant result. If you feed rats fresh fat, they grow much faster than if you feed them rancid fat. Have any of you ever had rancid fat? You have? No? Oh, I saw you nodding your head. Yeah, rancid fat is disgusting. Why would you eat it? Of course you're going to grow less if all you're being fed is rancid fat. So the difference in fat type is much greater than the difference here. That's why that shows up as significant. And then there's no interaction. Fat type has the same effect on both males and females. That's what the interaction is testing. The interaction tests, do males react to fat type differently than females do? But in this case, males are growing faster on fresh fat than rancid fat, so there's no interaction term. And we can see this if we graph it. So this is what the data actually look like if you make a graph. This is a graph generated in R. And the next thing we're going to do when we kind of have the concept down, we're going to go through and start live coding how this would look in R. But basically, you grow more if you are eating fresh fat than rancid fat, but males and females are not particularly different. One of the things that should strike you by this figure is the 95% confidence intervals are huge. And that's one of the difficulties with only having 3 samples, is that sample size, the bigger sample size gets, the smaller your 95% confidence intervals get, the easier it is to see differences. You'll also notice that the variances are not particularly equal. We haven't run a Levene's test on this yet, but we will need to do that. And we'll do that when we start doing the live coding. But it's basically saying, overall, the mean of fresh fat is higher than the mean of rancid fat, but males and females are not generally different from one another. Once again, the results of the analysis of variance should reflect what you see in figures. If the figures don't look like what the results in the Anova are, something's gone wrong somewhere along the way. All right. Do you feel you could calculate a two-way Anova if I gave it to you? Chances like, I don't know. Yeah.
I have a question about that.
Yeah. Mm-hmm.
Understanding.
Yeah, okay. Let's go back to that. So the F, it's the mean square of whatever the treatment is, in this case sex, divided by the mean squared residual or mean square within. That's what it is for that one. If you want to know what the effect of fat type is, then that is the mean squared for fat type divided by mean square residual. So, and then for the interaction, that is then the mean squared for the interaction divided by the mean square residual. Does that make sense? Yeah, okay. All right, 2 things we can do at this point, and it's up to you what we do. I've shown you how to calculate this. We can get practice calculating. If you want to run through the calculations by hand, I can be coming around and helping you with it as you go. Or we can go to live coding. If we go to live coding, I'll show you how to do it in R. But what I want you to do is I want you to work through this example by hand to make sure you fully understand what's going on with it. Do you want to do that work in class where I'm here to work with you, or do you want to do it as homework? No, we'll do live coding live because I think it's better to do that way. So the question is, do you want to take up class time working through it by hand, or do you want to just go ahead and start scripting? I can do either. I'm prepared to do either. Okay, then get to work. Start working this out by hand, pen and paper, calculator, or put it into a spreadsheet if that works better for you. But once again, in a spreadsheet, you need to be writing out the equations so that the spreadsheet isn't doing the work for you. It's just you're telling it to do the calculation, but you're telling it what calculation to do. All right, get to work, and I will help you when you need help. Yeah. Okay, so start with the raw data. So I would just put the raw data in somewhere, or if you want to just look at it off of your here. So the first thing you always have to do in any analysis is you have to generate means first. So you need to generate the mean for male fresh, the mean for male rancid, the mean for female fresh, the mean for female rancid, and then you also have to have the grand mean. And you can do the grand mean by either adding all those up and dividing by the total sample size, or in this case, because each of those is the same sample size, you can also just add up the means and divide by 4. You can't do that if the sample sizes are different. You have to then weight those. Does that help? Okay, sure. So that's always the first step. Haley, this is a good stepwise way of figuring things out. If you're going to do this, the first thing you need to do, generate the means. You need both the subgroup means and the grand mean. You need the subgroup means because subgroup means will be involved in calculating within sample variation. And you need subgroup means because they'll be used in calculating subgroup variation, sums of squares. And you need the grand mean for calculating total sums of squares. So, and then I would do these in this order because you need total, you need within. Total minus within will give you subgroup, although you can also calculate subgroup independently to check your math. And then the subgroup tells you how much is left over for these. So then calculating the treatment mean, and treatment mean then will tell you what the interaction is via subtracting these two from the subgroup. So having an order of things to do is helpful. And last time I didn't do them quite in that same order, but today I kind of did. So I've left you with the answers, but without any of the calculations. Question?
Did I write this one down right for that as subgroup? Or is that for a different?
Yes, for the subgroup, so each of the subgroup means, so you'll have 4
Minus the grand mean.
minus the grand mean squared. Yep.
And
But
times
then,
the number of
but then
replicates.
times the number of replicates because you have to weight each mean by the influence that it has on the data set as a whole.
Okay, so like if this one had 3, but then this one had 5.
Yep.
This one would be multiplied by 3, and that would be multiplied by 5.
Yep. Yep. In this case, you can just multiply the whole thing times 3 because they're the same sample size. But yeah, normally you would do it for each individual one if you had different sample sizes. And that makes sense because when you calculate how much variation is due to the different treatments, if one data set, if one subgroup has 3 observations and one has 10, one of them is going to be contributing much more to the sum of squares than the other. So you have to factor that in. Yep. That's the thing, when students mess this up on homework assignments, it's always forgetting to weight things by sample size. You're copying formulas. Good. That's the thing that Excel helps you do. It helps you work through things faster because you can just copy formulas. But of course, you have to know the right formula to copy. So in this case, you could do that. So in this case, because all the samples are the same size, you could just take you could do it this way. You could also do you could do it this way, or you could just sum all the data divided by the overall sample size, and they should all give you the same number. If, on the other hand, the means were made up of different numbers of samples, you would have to weight the column mean times the sample size of the column, weight this column mean times its sample size, and then divide that by because once again, the different numbers of observations are contributing differently to the overall mean. So yeah, so the grand mean really is, this is the truest definition of what the grand mean is. It's all the data divided by the total sample size. This is the grand mean. You can get at it these other ways, but you have to consider sample size while you're doing it. Once again, another problem that students have with calculating grand mean is in unequal sample sizes, they forget to weight things by sample size. So this is always the best way to do it because you have to think about sample size in these other ways. My first year biology class, when they have to calculate grand means for a problem like the one-way Anova, on their homework, they always mess up the grand mean. It's because I purposefully give them an experiment with unequal sample sizes. Are you calculating within sample variation? Yeah, okay, yeah, that's what it looks like. That's some squares within now, not total. You had it in the right spot a minute ago, and then you moved it.
So for SS within, we use the grand mean. No.
It's each individual
the-
value minus the grand mean squared for all the data. So where are we at here? So it's this minus the grand mean squared plus 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 that minus the grand mean squared plus that minus the grand mean, 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 that. All of those squared added up. That sums, oh, sorry, sum squares total or sum squares within?
Within, but I can
Oh,
do
sorry,
total too.
that's sum squares total.
Okay.
Sum squares within, rather than the grand mean, it's the sample mean. That minus that squared, that minus that squared, that minus that squared, plus that minus that squared, that minus that squared, that minus that squared.
Okay.
Yep.
Wait, so I do wait for this and then plus this
Yep.
with that.
So you want sum squares within for the entire data set. So you need what makes it within is you're looking at how these vary from the subgroup mean, how these vary from the subgroup mean, how these vary from the subgroup mean, how these vary from the subgroup mean. But because you have 4 subgroups, you will have within sample variation from this subgroup, within sample variation from this subgroup, within sample variation from this subgroup, and within sample variation from this subgroup. Those all get added up to give you your sum squares within for the entire experiment. Does that make sense? Okay, good.
The rows and columns.
So the row means minus the grand mean squared, once again weighted times however many observations are there, which is 6 in this case. So you have six items. These 6 items go into that row mean. These 6 items go into that row mean. And so it's the row mean minus the grand mean squared plus the row mean minus the grand mean squared. All of that added together and multiplied by 6. Once again, to control for sample size. So here it is, one sums of the squares plus the other sum of the squares multiplied times 6. It's the same thing, except just with the columns. Yep. Stays at 6 because you have two treatments and three observations in each treatment.
I'm in the subgroup and I'm getting just like slightly
That's rounding error.
off.
That's just
Oh.
rounding error.
Okay,
How far off is it?
like 20, and then like the decimal's well off, but that's what I got.
That's more than rounding error.
Yeah,
That is more than rounding error.
I don't
Let's see.
know.
Where
'Cause I like rechecked if I typed it all in right.
where are your sub?
I had the blue ones.
Okay, all right, hold on. I guess it could be rounding error since it all gets squared, but that just seems high to me.
I just wrote this down wrong.
Oh, you wrote something down wrong. Okay,
But
right.
no, but that shouldn't have anything to do with the subgroups. The row mean. That is
So
just
what are you? This is the
subgroup.
subgroup means. Oh yeah, because you don't use row means in the.
Yeah.
Yeah.
I
Okay.
just realized it while I was looking at that.
Yeah. Yeah. Plug it into. You have a spreadsheet.
I can pull one.
Just to check your math. Put your subgroup means in. 695.67. 535.33. 642.67. 517.33. Okay, now put the grand mean next to them, in the column next to them. 597.75. Copy that down. Okay, right now in the next column, subtract one column from the other column and square it. Okay, drag those. Oh, yep. Now multiply, sum that whole thing. And multiply it times 6.
Oh, times 6. Wait, I thought it was times 3.
Oh, sorry, times 3.
Okay.
Times
So
3.
then
Times
that's
3.
what I'm doing completely wrong.
Times 3, no.
Then that's completely different than what I figured.
Yeah, and that's also different from what I
Yeah,
got.
that's.
That's weird. Yeah, it's all just rounding because those are all correct, right?
I could like individually do them. I did them in like a big line. I could like individually do them.
Yeah, so the difference between yours and mine is because I'm doing it in a spreadsheet. Let's see. I'm carrying everything out all the way, and it just does it automatically. I've had it round just to make it easier to view, and so that's the difference.
Okay, gotcha.
On your homeworks, when you do them by hand, when I see things that are really wrong, I have to go through and figure them out using the rounding to make sure that it really is just a rounding error. But when the computer does it, it's carrying all those digits, all those decimal points, and when you do it in a spreadsheet, it's also doing that.
Row times column.
Okay, you can figure that out simply by subtraction. So you would subtract the sum scores rows and sum scores columns from the sum scores of subgroups. So to get this, you can think of it this way. Take this part of this table, take the subgroup, subtract the effective treatment 1, subtract the effective treatment 2, and whatever is left over is the interaction term. And that's way easier than calculating it directly. Yeah.
So for the row mean, is it, so it's these two and then
Nope, it's your row mean minus your grand mean squared, and the row mean minus the grand mean squared, and then that all weighted by 6.
by 6?
Yep, because you have 6 observations going into each mean. Okay, that seems right. That seems right. And then you take those two things and add them together.
Oh.
Ha ha. There you go. Not a problem. Yeah.
So if I do the SS subgroups,
Subgroups minus.
the rows
Mm-hmm.
minus the columns,
Mm-hmm.
I get negative 36,000.
Well, that's because something's wrong somewhere. Clearly. Why is your subgroup so much different than mine? Oh, it's because you didn't weight it by sample size. Oh, no, you did weight it by sample size. Wait.
Oh, it's this one.
It's that one.
Uh,
You put it in bold. You need to pay attention to your own annotations. Yeah, chance.
yeah, row by column. So
Okay.
subgroup,
Minus the sum scores row minus sum scores column.
okay.
So where's your subgroup?
Okay.
Sum scores. Where's your sum score subgroup?
No, I guess I don't have a subgroup.
Why don't you have a sum score subgroup?
That's a great question.
You have subgroup means. Yeah, so you need to calculate that. Yeah.
Okay.
That's why I put this as the third thing that you need to calculate, because you need to calculate this in order to subtract this and that to get that.
SS total is this with the green.
Mm-hmm.
Okay.
For everything.
Okay.
For everything. Yep.
And then
Subgroup means are this mean minus the grand mean squared times that mean times minus this grand mean. Sorry, no, I said times. I meant. So that minus grand mean squared, 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 all multiplied times 3 because you have 3 observations making each of those comparisons. So the subgroups are squared. Yep.
what were you saying?
So yeah, so by subgroup we mean you really have 4 subgroups. You have male rancid, male fresh, female rancid, and female fresh. And so the subgroup means are based on those 4 means rather than the row means, which are based on 2 means, and the column means that are based on 2 means.
So you said 3 observations.
Yep, because you have 3 observations for this mean, 3 observations for that mean, 3 observations for that mean, 3 observations for that mean. Yep.
Right.
In the same way when you were doing the sum of squares rows, it was 6 because you have 6 observations going into that row mean, 6 observations going into that row mean.
Okay.
Does that make sense? Good. Figuring out the multiplier, you have to think about what's going into calculating that mean. That's the thing that you multiply times. Would that help, Chance?
Yeah.
Okay, good. Yeah.
So my sum of squares within that is way off.
Okay, show me how you calculate it.
I took for each value minus this subgroup mean squared. And then
Okay, so. Okay, let's see. So many colors. What just happened? I did, but that was a smaller value than before, wasn't it? 1166.67 is what I got.
Oh, I'm looking at the wrong value on here.
Yeah, it's this, and this all add up to be that. Yep.
Oh, gotcha.
Yep. So I just to keep myself straight, rather than doing it all in one big line where I'm prone to probably mess something up in that long big string of things, I did mine for, this is male fresh, male rancid, female fresh, female rancid, and then added them all up. Yep. Right.
For your p-values, did you just like put them in a Daniel-Silver's calculator?
Yeah, actually I ran it in R. But yeah, you could do it that way. All right, we're out of time. You guys are so caught up in the fun of working a two-way ANOVA by hand that you have lost track of time. Finish this up between now and Friday. Come back with any questions you might have. Homework for Friday, since we didn't do any live scripting today, is a normal analysis of variance is the dependent variable tilde the independent variable, data equals data frame. How would you alter this syntax to turn a one-way ANOVA into a two-way ANOVA? So this is how you do it for a one-way ANOVA. You have a dependent variable and one independent variable. How would you alter this to make it a two-way ANOVA? And the other thing that I want you to do is I want you to take the data set that you have in front of you right now and put it in a format that will be analyzable easily in R. Walk into class ready to tackle live coding of a two-way ANOVA with a data set that you yourself set up. Remember that R likes data in long form rather than wide format. Long format versus wide format. And that's it. I'll see you guys on Friday.